rocket A, we have 2 grams of petrol, and in rocket B, we have 2 grams of hydrogen. And we're going to find out which produces the biggest bang. Serious science, this. So, first up, petrol. Lovely, explodey petrol. Okay, and now, hydrogen. It's a clear win for hydrogen.
Hydrogen. It's the ultimate sustainable, eco-friendly energy source of the future. So, how will hydrogen energy transform our world? Are fuel cell electric vehicles truly safe? In Part 4, let's delve into the truth and misconceptions of fuel cell electric vehicles. Is there any chance that the hydrogen used for fuel cell electric vehicles could explode? Despite the preconception that hydrogen is dangerous, it is in fact safer than other fuels. The auto-ignition temperature of hydrogen is higher than that of gasoline or diesel, and since it is 14 times lighter than air, it disperses quickly into the atmosphere. Therefore, even if there is a leakage, the chances of it leading to a fire or explosion are very low. In other words, hydrogen disperses quickly into the air, lowering the possibility of combustion, making it relatively safer than other fuels. Does that mean there is no danger of hydrogen exploding? No. All gases have the risk of exploding depending on pressure. However, we are already using high-pressure gases, such as liquefied petroleum gas and compressed natural gas in our daily lives. That means that if we adhere to basic safety precautions, there won't be any problems. In the case of hydrogen, there is no danger in its gas form, but in order to increase its efficiency, a tremendous amount of pressure is applied to it, 700-fold of atmospheric pressure. The higher the pressure, the higher the risk of explosion. But as long as safety precautions are taken, using hydrogen is entirely safe. Since steel fuel tanks can explode in extremely hot flames. Hydrogen fuel tanks are made of carbon fiber reinforced plastic, which is 10 times stronger than steel. In addition, fireproof material is applied to both the inside and outside surfaces. And when exposed to flame, safety valves release the internal pressure quickly to ensure safety. However, in the event of a fire, the tank will be damaged by hot flames, regardless of its material type. But instead of exploding, a hydrogen tank made with carbon fiber reinforced plastic, which is basically like thread, will rip apart when hit with great force, causing the hydrogen to quickly disperse into the air. Let's examine how safe Hyundai's fuel cell electric vehicle, Nexo, is. All fuel cell electric vehicles currently sold in South Korea have passed the Korea Transportation Safety Authority's assessment test, as well as the UK's Vehicle Certification Agency's safety test. They have also passed the Vehicle Safety Test and Hydrogen Tank certifications of Germany's Technical Inspection Association, the TÜV. Also in 2018, Nexo was chosen as the safest SUV in Europe and the first to receive a Top Safety Pick Plus in a collision test by a U.S. nonprofit Vehicle Safety Institute. Nexo received Good, the highest rating, in 6 rating categories that included moderate overlap front, driver side small overlap front, passenger side small overlap front, side roof strength, head restraint, and seat. Additionally, it is undergoing several hydrogen fuel tank safety assessments, including burst, drop, flame, and extreme temperature tests. Now that the safety of fuel cell electric vehicles is validated, it's time for the entire world to race full speed ahead into an age of fuel cell electric vehicles. Why don't we go take one out for a spin? But first, we need to fuel up. You might wonder, are hydrogen stations safe? Most hydrogen-related accidents are due to inadequate maintenance. Just like gasoline or LPG fueling stations, hydrogen fueling stations are subject to strict safety regulations and can be operated without any major risks. As of 2019, there were approximately 370 hydrogen stations worldwide. The fact that hydrogen stations are being built in central Berlin, Germany, the Tokyo Tower in Japan, and the National Assembly in South Korea means its safety has been proven. The age of fuel cell electric vehicles is fast approaching. They are the future of automotive transportation. Fuel cell electric vehicles are eco-friendly, economical, and safe. If your next choice is a fuel cell electric vehicle, a brighter future will unfold.
With all these safety systems in place, it's extremely unlikely that these vehicles would leak much fuel, and even less likely that a leak would result in fire. The controlled simulation you're about to see shows the result of the failure of one system, the pressure relief device. Though experience with natural gas has shown that a failure of the pressure relief device is extremely rare, the results of such a failure would appear like this. In this demonstration, fuel was purposely leaked and ignited by an electric spark, in both a car fueled with hydrogen and a car fueled with gasoline. The hydrogen tank empties in less than 2 minutes, and the flame goes out with virtually no damage to the vehicle. Inside the rear window, the temperature rose only 13 degrees Fahrenheit, and at the steering wheel, the temperature barely went up at all. The reality is that safe design makes this kind of an event highly unlikely for any kind of vehicle.
So let's take a look at the reaction of hydrogen and oxygen. My hearing is bad enough, so I'm going to put these on, just so I don't have to hold my fingers in my ear. There's a seal to keep the hydrogen in, and actually I filled it from the bottom, so there's a little opening on the bottom. I'm going to take that off. And now, on the top here, I have an opening. If I light this, let's light this baby. What happened? What do you think was going to happen? What do you think was going to happen? Well, you've seen the hydrogen-oxygen reaction before. But remember that in order for hydrogen and oxygen to react together, we got to have both hydrogen and oxygen. If I have a can filled with hydrogen without oxygen, we can't have a reaction. I only get a reaction where the hydrogen escapes from the can. As the hydrogen was escaping out the top of the can, what was going in the bottom to replace it? Oxygen. Well, air, and that air contains oxygen. So as the concentration of hydrogen in the can was going down, the concentration of oxygen in the can was going up, and eventually we reached a point called the explosion limit. And when the ratio of hydrogen to oxygen got to a certain point, then the reaction between them occurred very rapidly, and we got the familiar combustion, the familiar explosion reaction. All right, so you just got your first lesson. The reaction rate, or the rate of a chemical reaction, is going to be dependent on the concentrations of the reactants.
Gaseous hydrogen is transported in tube trailers. The cylinders on those trailers typically transport hydrogen at 2400 psi, although some special permitted types can transport hydrogen at 6000 psi or more. Future technologies may allow for even higher pressures. These cylinders are either a Type 1, constructed of steel, or a Type 3 with a steel or aluminum liner and a carbon fiber overwrap. High-pressure cylinders are constructed and tested to very rigorous safety standards and have a leak before burst design. They are also equipped with pressure relief devices. While steel cylinders have burst discs and standard PRDs, composite cylinders have a thermally activated pressure relief device. In the event of fire, the TPRD is designed to melt open and release the entire contents of the cylinder. Stations that receive gaseous hydrogen as their supply can be replenished a few ways, either by swapping an empty tube trailer for a full one, swapping banks of cylinders, or by refilling the stationary cylinders. Liquid hydrogen, due to its negative 423 degree Fahrenheit temperature, is transported in low-pressure cryogenic trailers. The tank construction is similar to a thermos bottle. It is a double-walled steel container with a vacuum-insulated space in between. Integrated features include vents and reseatable overpressure relief devices. Should the head pressure in the tank rise above safe levels due to the liquid hydrogen warming and returning to its gaseous state, the PRDs will activate.
This prop provides a side-by-side demonstration of the flame characteristics of hydrogen and propane. It consists of two burners fed by two cylinders. One cylinder contains gaseous hydrogen, and the other contains liquid propane. The gas pressures and flows have been adjusted to make the flames similar in size. Temperatures at the base of each flame and at the top of each flame are measured using thermocouples, allowing us to compare the relative temperatures of hydrogen and propane flames. Here we have the propane and hydrogen flames burning on a bright sunny day. The orange propane flame is clearly visible. The hydrogen flame is nearly invisible. But when we look at the flames through a thermal imaging camera, we can see both flames clearly. A pure hydrogen flame has low radiant heat, much less than the amount of heat radiated from the burning of conventional fuels. Here we measure the lower thermocouple readings at just over 500 degrees Fahrenheit for both the hydrogen and propane flames. At the same time, the readings at the middle and upper thermocouples show a lower temperature and a greater difference between the two flames. Now, let's do the same demonstration in the dark, at night. We are in the same location that we used in the daytime. You can see that the same landmarks are visible. In the dark, both flames are clearly visible without a thermal imaging camera.